You did an investigation looking at polynomials and what they looked like, how we named them, and relationships between different characteristics. So just a couple of reminders that when you name a polynomial by the number of terms, if the polynomial is one term, we named it a monomial, two terms, a binomial, three terms, a trinomial, and four terms after that, so 4 plus, I guess we should say, we're just going to call it a polynomial. Sometimes they'll say of a certain amount of terms. For degree, if the degree was 0, so it had no x's in the equation, we named it as constant. If the degree was 1, so it's x to the first power as the highest, it's linear. If the degree is 2, it was quadratic. 3 is cubic. 4 is quartic. 5 is quintic. And 6 plus, you're just going to write a polynomial. Actually, depends. It could be a binomial, whatever, of degree, and then list the degree, but you don't have to have a special name for it anymore. So other things that you should have concluded from the investigation. How is the degree related to the maximum number of turning points? So just a couple of ideas for pattern here. A line was degree 1, but the turns was 0. A quadratic is degree 2, but the turns is 1. A cubic is degree 3, and then we had to start getting a little careful. It might look like this, but it could also look very like this with some deeper little turning points there. And so the turns could be up to 2, but could stay below it. So that's why it doesn't just say the number of turning points, the maximum number of turning points is equal to 1 less than the degree. So the degree minus 1. How is the degree related to the end behavior? So hopefully you guys saw, and I'll just use what I have here, that when the degree was odd, the ends went in different directions, whereas when the degree was even, the ends went in the same direction. So if we have an even degree, we have the same end behavior on both ends. And if we have an odd degree, we have different end behavior on both ends. One goes up and one goes down. So how is degree related to the maximum number of x-intercepts? So if we look at, again, a line, but we put it on the axis, the line will cross the x-axis one time unless it's horizontal, and that's kind of a special case, that constant. A parabola might cross the x-axis twice, but it might not cross at all, and there's a way for it to have exactly one solution as well. So again, that's why this says maximum. Okay. A cubic will definitely cross because the ends go different directions, but it might just cross once, or it might cross 3 times because of those 2 turning points. So again, we can't tell you exactly how many times it's going to cross, but we can tell you the most times that it could cross. So the maximum number of solutions, or x-intercepts, is equal to the degree. So these were conclusions we should have seen in the investigation. So There's a lot of semantics here. A lot of ways to write things is going to kind of be the focus of the lesson, putting this stuff together. The knowledge here is pretty good. Usually people don't struggle with it, but then labeling some of the things is a little bit difficult with notation. So the first thing I want to talk about is writing a polynomial in standard form. We would take something like this and write it in order of the terms, combining any terms that are like from highest degree to lowest degree. And then this polynomial will have two names, one by the degree and one by the number of terms. So based on the number of terms, we would just consider this one a polynomial because it's more than 3 terms. And, oops, sorry, it's in the wrong spot. And then based on the degree, the highest degree here is 3. So remember, each of these terms has their own degree, and then the polynomial overall has the degree of the highest term, which is 3, which would make it a cubic. So we would call this a cubic polynomial. Now in these next questions, I want to be really careful because we talk about even or odd, and you guys are going to talk about this again in pre-calc. We are not saying that the function is even or odd here. We are focusing on degree. So it's very important that we make this distinction that we are specifically talking about degree. So how can we tell? Sorry, and these should continue on. Notice that the ends for this first function go both up. Same for the second one. Okay, I would know that both of these have even degree. Whereas the third one, the ends go in different directions, I would expect this to have an odd degree. Then the estimated turning points. So in this one, there are 3, and you're just estimating here. To find exact turning points, we would either need the polynomial written in like a factored form or be able to factor it ourselves, or we'd need some technology. So we're just estimating. So this turning point down here looks like it's at about -2.5, and then 1, 2, 3, 4, -4.5. Then there's another one up here that looks like it's at 1.5, 2.5. And then there's one more here that looks like it's at 3, 0. Now the next thing we want to talk about are increasing and decreasing intervals. So remember, and I'll just highlight them in different colors, we go from left to right across the function. So here I'm decreasing, I hit the turning point, then I increase. Then I hit a new turning point and I decrease again. Then I hit the next turning point and I increase. So what I have here is everything that would be part of the decreasing interval, I've highlighted in blue, and everything that would be part of the increasing interval, I've highlighted in yellow. So my increasing interval, notice it goes from this turning point to this turning point. And remember, we list these with x values in interval notation. So my increasing interval appears to go from -2.5 until +1.5. But then there's another increasing interval after this turning point going this way, and that is from a value of 3, and then it infinitely is increasing. And we put a U between sets when we want to include both of them, kind of like putting that or in between the inequalities. For the decreasing interval, we want to look at the blue highlighted areas. So this first blue highlighted area, if we are thinking x values, that's from -infinity up until this first turning point that was about -2.5. So from -infinity until -2.5. And then there is another decreasing interval from 1.5 until 3. And again, because there's 2 of them and we want to include both, we use that symbol between them. Now the end behavior, we want to look at the directions the ends are going, but you basically have to be able to say it like this: what's happening on the left and what's happening on the right, but there's going to be some weird notation. So on the left, this would be the left side of our function. Notice that after all the turning is done, this function is just going to go up towards infinity on the left side. That's kind of the direction it's headed when all the different special stuff about the function is done. So the left side goes towards infinity. On the right side, it also goes upward after all the turning is done, so it also goes to infinity. So it goes up on the left and up on the right, or a better way to say that is it goes towards infinity on the left and it goes towards infinity on the right. And then we want to say this with some special notation. So this is where it might get a little hard. Remember, for end behavior, you're always making two statements because there are two ends. And so we would say as x goes to negative infinity. This is left, okay? Because that means this, as your x values get infinitely smaller, y goes to infinity. Then you're telling me the y values get higher, okay? I can say the right side by saying as x goes to positive infinity, and then I say y also goes to infinity. All right, so we're going to go ahead and look at these other ones the same way. So in this next one, estimated turning points, I marked them on my paper, so this looks like negative 3.5, 1.5. And again, we are actually estimating here, which is not something we always do, but in this unit, you'll see we're a lot less exact and more just about shape and end behavior, some basic ideas of the function. So this next one looks like it's at 1, 5. And then this last one looks like it's at 3 and then half. And then remember, our increasing and decreasing intervals are based on those x values in those turning points, because you're doing one thing until you turn around. So the first thing I'm doing is decreasing from left to right. So from negative infinity until that first x value in the turning point, I'm decreasing. Then I hit the turning point and I'm increasing. So then my increasing interval is from the x coordinate of that first turning point until the x coordinate of the second turning point. Then I hit the turning point and I'm decreasing again. So another section for the decreasing interval from that 1.5 until that value of 3. And then I turn around again and I'm increasing, and that's from 3, and it doesn't turn around again, so that will have that behavior infinitely. For the end behavior here, it's the same as the last one. The left side's going towards infinity. So kind of a helpful hint here, I can write these statements right away, and then I can figure out what's happening to y. Like, this is automatic. Every time I'm going to make a statement about the left and a statement about the right, and my job is to figure out what's happening to y. On the left, it's going to infinity, and on the right, it's going towards infinity. The last one that we knew was odd degree here. I see 2 turning points, and I'm going to estimate that first one to be at 1.25, maybe 1 1/4, and then its height is at 5. And then there's another one at 3.5, 0. And so my first interval here, I'm going to say is increase. And I know that's an increasing interval because as from left to right, I would be increasing for the entire function until I reach this first point. So my increasing interval is going to start us off from negative infinity till that first starting or turning point, which has an x value at 1.25. Then I hit the turning point and I have a decreasing interval. So my decreasing interval goes from one turning point, x value of 1.25, to the next turning point, x value of 3.5. Then I hit this turning point and I'm increasing. So that's going to be added on to my increasing interval from 3.5 to infinity. Lastly, we're going to write the end behavior. So again, we can start our statements that we know means on the left side, the y values are doing what? And on the right side, the y values are doing what? And on the left side here, I see that the graph, after twisting and turning on the left, goes infinitely downward. So the y values would be going down, so that's negative infinity. And on the right, they are going up, So that's positive infinity.